Hi everyone, welcome to the third introductory video for research design and analysis. Today we're going to be talking about the fundamentals of statistical inference and introducing some of the logic of hypothesis tests. So as a reminder, right, when we're talking about statistical inference, we're always thinking about studying populations, but in order to study those populations, we don't have access to everybody, so we have to take a sample. And this sampling procedure is much like sampling procedures anywhere else, right? So you might, for instance, have had a sample of a beer when you're out at the pub with your friends or something, right? And you're not sure if you want to order a whole beer, so you might order a taster, right? You might get something smaller in order to sample it and then make a decision about what the full beer is going to taste like. So, well, the logic of this assumption then, right, is that our sample represents the population. In this case, the small taster that you got, right, is representative of what the larger beer is going to taste like. It clearly wouldn't be a good taster if the sample that you got tasted totally different than what the full beer is going to taste like. And obviously that's, bad from a sampling beer perspective, but it's something that we really have to keep in mind when we're designing research studies and think about, okay, how well does our sample represent the population and how much variability is there from one sample to the next? Because from one pour of beer to the next, there's not a whole lot of variability. But from one person to the next, there's an awful lot of variability that we have to take into account. And that means that we're going to have to think about larger and larger samples in order to generalize back to our population with greater and greater certainty. So when we're studying the population, right, we're just talking about studying parameters because parameters are characteristics of the population, and these are usually things that are theoretically meaningful in some way. So for instance, it might be the mean value for a group of people. It might be the mean difference between a group of people, right? But it really can be any kind of statistic we might want to compute. It is just some characteristic of the population, right? So for example, what's the average height of college students? How many attempts does it take a healthy rat to learn a maze? What's the correlation between height and stroke power for rowers, right? These would all be empirical research questions where we're going to take a sample of individuals and make some generalization from the sample back to the population. And that's the inference, right? Because we're infer that what we observe in the sample is going to hold for the population. So the statistics then, right, when we use the term statistic, these are mathematical values computed from the data. So for instance, the mean is a statistic that we might calculate. And then there's a difference there between the statistic and its value, right? So the mean is the statistic, but the mean height might be a particular value, right? Or the median height might be a particular value, where again, the median is a statistic, but then it can take a particular value when describing a sample. So usually these types of statistics are going to serve one of two functions when we calculate them in the sample. We're going to have things that are sort of purely descriptive statistics where they summarize some aspect of the sample data. So this would be your means, your medians, your modes, right? Standard deviations, variance, any of those kinds of things. Now, there's the kind of a continuum here when we get into then inferential statistics. And inferential statistics aid the testing of a hypothesis in some way, where we're trying to make some estimate about the population. So inferential statistics usually have some kind of uncertainty value attached to them. So for instance, we might say that the mean in our sample was 10, but there's a 95% confidence interval of, with a margin of error of 5. So the lower bound of that confidence interval is 5, the upper bound of that confidence interval is 15, and it's centered around our mean in the sample, which was 10. And we'll get into more detail about confidence intervals in later presentations, right? But the general idea here is that descriptive statistics are just being applied to the sample. Inferential statistics are making some kind of inference about the sample back to the population. And they're very much intertwined, but this is still a useful distinction to make, I think, especially when we're starting out in statistics. So first, let's talk about some descriptive statistics. So they summarize some aspects of the data that we currently have, right? The data that are in front of us in the sample. So this, could be any measure of central tendency, like a mean or a median, or it could be some measure of spread, like a range, quartiles, or the standard deviation. These are used mostly for describing data. So we don't make inferences about the population from these values alone, but they are often the first step in data analysis. And they're also really useful if the sample is all that you're interested in, right? So for instance, if I want to know, the descriptive statistics of my class, and I'm not really worried about generalizing from my class, to the larger population, then essentially my sample is the population. Because if it's all I care about, then I just need to look at the average and say, yep, that's what the average age is. Inferential statistics, on the other hand, right, aid the testing of some kind of hypothesis about the population. And we're going to introduce kind of the logic of hypothesis testing in this video. It's going to indicate how reliable an effect in the sample is, which is to say, do we think that this is something that is going to be relatively robust and at least in a qualitative sense kind of hold up from samples to samples so that, in kind of the grand scheme of things, it would hold up in the general population. So how likely is the effect to be observed in the population is ultimately what we would like to know. And this value, generally has no physical meaning when we're calculating these inferential statistics. So it's not like the mean, which we'll describe in, inches or seconds or meters or something like that. But it will be in units of probability. So we'll have probability distributions that we might describe how far along on a probability distribution a particular observation is. So for examples, we have t distributions, f distributions, chi-squared distributions, right? These are all things that we could calculate as inferential statistics. Similarly, we might have things like eta, tau, or beta being, a regression coefficient, where we can then say, okay, how likely is this beta, assuming that the true beta was 0, right? And these are all things that we can test inferentially. So the basic logic of inferential statistics means that we're going to start with two hypotheses. We're going to have a null hypothesis where we assume there is no effect of the independent variable. So that could mean that there is no relationship between two things, or that there's no difference between two sample means, right? Whether it's phrased as kind of mean differences or correlations, we're going to be assuming that there is no relationship most of the time with our null hypothesis. We can choose other values, but as a starting point, we're going to say that there's no relationship. And then we're going to have some alternative hypothesis, which has to cover the rest of the probability space. So if our null hypothesis is that there's no difference, right, our alternative hypothesis would have to be, well, maybe there is some difference, right? There's some effect of the independent variable. We can't say what it is it positive, is it negative, but we don't think it's 0, right? So this would be a type of null and alternative hypothesis that you could use. So we start by pretending that the null hypothesis is true in frequentist statistics. So we're going to say, how likely is our observed statistic if the null is true, right? And all of our other assumptions kind of hold. If our assumption is unlikely, given the null, then we will reject the null and say that there is an effect. So to give you an example of this, let's say we're playing a game of Dungeons and Dragons and I have my 20-sided dice here. Right? So in Dungeons & Dragons, rolling higher numbers is generally good. So rolling a 20 is basically the best roll that you can have, right? So if you see me roll a 20, you have to, do you wonder if I have a fair dice or not? And if you only get to see me roll one die, that's kind of hard to determine, because assuming that the die is fair, the probability of getting any value is 1 in 20. So all values have an equal probability of coming up on a 20-sided die. So if you just see me roll 120, you can't really say, oh, I think he's cheating, or maybe he just got lucky and he had a good roll there, because the probability is the same as if I had gotten a 14 or if I had gotten a 2. But let's assume that I'm a cagey cheater, okay? So I don't want my dice to come up 20 every time, because obviously that's going to be really easy to spot. If I roll 3 20s in a row, that has a probability of 1 in 20 times 1 in 20 times 1 in 20, right? So it can still happen, but if you see me rolling 3 20s in a row multiple times, you're going to get suspicious really fast. Right? So let's instead say that I've weighted my dice so that it doesn't come up 20 every time, but that higher numbers come up more often. So you've watched me roll my die 10 times, and the average value on those 10 rolls was 14. So you're going to go home and you're going to roll your die, which you know is fair. So you're going to roll it 10 times and calculate the mean. And you're going to do that 1,000 times. Let's say you've got a lot of time on your hands in this situation, right? But each time you're going to record the mean of your 10 rolls. So you're going to have a distribution of 1,000 sample means where the size of the sample was 10. And what this will give you is a distribution of sample means, shown here, that you then have for a fair die roll. So assuming a fair die roll, right, on average, you should have an expected value of 10.5, which is just the average of the digits on the die, 1 to 20, right? And that checks out. And then you can establish some variability where you're saying, okay, if I'm taking samples of 10, here's how the mean of 10 die rolls should be distributed. Most of them, right, should kind of fall between 8 and 12, centered around 10.5. Now, if I got 14, right, it's pretty unlikely to have gotten a mean value of 14 on 10 die rolls. It's not impossible, but it's pretty unlikely. So how unlikely does it need to be before you say, hey, I think you're cheating, right? Obviously, that's a big deal. There's some costs to calling me a cheater. It might end our friendship, right? If nothing else, it's going to make for a pretty cold game night the rest of that night. So if you see that I've rolled a 14 on 10 die rolls, oh man, it's unusual, it's unlikely, but do you really want to stand up and say that you think I'm cheating in this situation? There's a cost to saying that you don't think that my die is fair. And if I'm an even more careful cheater, I might rig my die to be more subtle so that in 10 rolls, the average value is 12, right? So now you can see that would put me in this bin. So getting an average value of 12 is still, statistically a little bit odd, but it's not that unusual, right? It's pretty close to what we would actually expect on a fair die. So, there's a chance that I'm cheating here. It's a little bit unusual given a fair die, but it's not that unusual, right? So between a 12 and a 14, right? If I see a 14, I'm probably more likely to think that's a really unusual value for 10 die rolls. Whereas if I get a 12, I'm probably more likely to say, well, he's probably just getting lucky. He's on a hot streak. I don't think he's actually cheating because that's something that could happen on a fair die, well, a reasonable proportion of the time, right? And in essence, this is what our statistical inference is all about. The distribution that you have established through your fair die rolls is the null distribution. This is the distribution of sample means if we assume the fair die, right? We assume there is no cheating, making it the null hypothesis, right? So then we see how unusual was the observation. You saw me get an average of 12 on 10 die rolls under that null hypothesis. And in this case, it's not that unusual under the null hypothesis. If you saw me get an average of 14 on 10 die rolls, that's much more unusual under the null hypothesis. It certainly can still happen, right? But it's pretty unusual. So if you observed this, you might actually reject the null and say, hey, I don't think that die is fair. Okay, so this gives you a general introduction to how we're going to be drawing inferences from distributions. Die rolling is a good example because it's something we're all kind of familiar with and can visualize, but we'll be working with other different types of distributions as we move forward. But the key logic stays the same. If we know something about how the sample statistics should be distributed, right, like that distribution of sample means we were just looking at, then we can make inferential judgments about our sample statistic. Right? So with like coin flips, we could say we should expect X number of heads in K number of coin flips, right? It should be centered at about half, right? Because half the time on a fair coin, we should be getting heads. But as we flip more and more coins, it's not going to be unusual to get some big runs of heads or some big runs of tails, and we could establish a distribution of the probability for different numbers of heads. Similarly, we could say, well, we expect a mean to be this large or larger X% of the time under the null hypothesis, right? So we can say if this is the distribution of sample means, we can talk about what a typical mean would be, right? Kind of right at the expected value. And we can talk about what unusual means might be, very low or very high. And if our means are sufficiently unusual, we might reject the null hypothesis and say, well, we don't actually think these data came from this distribution. We think there's something else systematic going on here. And what we observed is not due to sampling variability by itself. So this is, again, just a general introduction, and we'll be delving into each of these things in more detail as we go. But the thing I want to emphasize here, right, is that we're going to take these descriptive statistics in our sample, right, be they means and medians, standard deviations or ranges, right, and we will be weighting the effect that we observe in conjunction with the sample size against the variance. And then the balance of these two things, right, on the effect size and the sample size kind of giving us more certainty toward what we're seeing, the variance giving us less certainty toward what we're seeing, are going to tilt about this fulcrum. And that fulcrum is the mathematics of the inferential statistics. And that's where we're going to have to decide, how extreme does a value need to be before we reject the null hypothesis? Because under the null hypothesis, we're going to make some assumption about what the distribution of, for instance, sample means should look like, right? And then if the value that we observed was highly unusual given that distribution, we're going to say that didn't happen by chance alone, right? Or we don't think that that happened by sampling variability alone. We think there's a real effect there, right? You're going to look at my my average value of 14 on 10 die rolls, and you're going to say that you think I'm cheating. But the threshold at which you make that decision is determined by these inferential statistics. And at times we can be more liberal in saying that there's a difference there, and at times we can be more conservative in saying that there's a difference there. And so our choice of exactly where to position this fulcrum in terms of how much evidence we need before we declare an effect depends on how liberal or conservative we want to be in making that decision.